Today we're going to wrap up indexes and talk about some remaining details that I kind of glossed over with B plus trees. So how do we maintain balance in a B plus tree when things are added and deleted, and just some more details on how they're constructed and maintained. And then we'll talk about spatial data, so things like GPS coordinates and addresses, things representing points in space. How does a database efficiently store and retrieve spatial information? So one detail I've left out on B plus trees so far is there's this rule that all nodes have to be greater than or equal to 50% full at all times, with the one exception of the root node. So let's look at this node here. It's 2/3 full, so that's greater than 50% full, so it's okay. This one is totally full, so it's okay. The root node is less than 50% full, but that's okay, and it has to be because there's no other way to represent this tree. And imagine if we only had one node, so the only node that exists is the root node. If we add the very first item, obviously it has to be less than 50% full in order to be able to hold just one item. So why do we have this rule? Well, let's take a look at an example here. Let's say that I were to delete some things from those nodes from the previous page. So these two leaf nodes down here now are violating that rule. They are less than 50% full. And this tree is using many more nodes than it needs to be, many more disk pages than it needs to be. So we're using up 3 disk pages to represent just 2 items. We don't actually need this parent node at all, because if we were to just merge these 2 leaf nodes together, like over here, then we end up with just one node to represent the entire tree. And now we can access anything in just one disk page rather than needlessly having to access 2 disk pages to find any given item. So once we merge those 2 nodes, now this is 2/3 full, so it's no longer violating the rule. This rule is basically just to keep the height of the tree low in order to avoid accessing more disk pages than needed. So what does half full mean, though? It's different for internal nodes than it is for leaf nodes. For internal nodes, it's defined by the branching factor. So if the branching factor is b, then the node needs to have at least b/2 pointers in it in order to be considered half full. So let's look at this first node where the branching factor is 4, so 4 pointers in this node. And 2 of them are used, so this node is considered half full. Even though it only has 1 out of 3 possible keys, it's not considered 1/3 full, it's considered 1/2 full since it's based on number of pointers. And this bottom node, where the branching factor is 5, I now need to have 2 keys in order to get up to 3 pointers. So 3/5 is greater than half full. For leaf nodes don't have pointers. They are just storing values. So it's just based on the maximum number of values that the leaf node can hold. So if k is the maximum capacity of the node in terms of number of values, then we need at least k/2 values. So in this leaf node, since k is 3, which is an odd number, we need 2/3. It's always going to be greater than half full for an odd number. But in this case down here, it's exactly half full, 2/4. So these 2 nodes, even though they have the same number of items in them, those are the minimum required in order to maintain greater than or equal to 50% full for those 2 examples. So how do we enforce this 50% full rule when adding and removing things from the tree? Let's start with add, since it's easier. You always have to start somewhere, so there's going to be an empty tree at some point before you've added the first item, and that's why the root node is exempt from this rule. So we'll start with an empty root node. It's obviously less than half full, and then after adding the first item, we put it into the root node, and it's only 1/3 full, but it's okay since it's the root. And when adding additional items, we always try to find an existing node to add them to. So if we add B and C, they're going to go into that same root node. And now the root node is full. So if we try to add D, we can't put it in an existing node, we have to make a new one. And if we just made another new node over here, and then put D in it, then this one is no longer the root node. In order for this to be a tree, we're going to have to kind of make a new parent node of these two. So what that means is this is not allowed. We can't put D over there by itself into its own brand new node. So what we have to do is redistribute A, B, C, and D into these two nodes such that both of them remain greater than or equal to 50% full after the redistribution. So let's see how that looks. I have two cases here. One where K, the max capacity, is an even number, 2, and one where it's an odd number, 3. So when it's an even number, it's trivial to see that we can take a full node and split it into two nodes and redistribute all of the items such that the two nodes are both half full. So even if we weren't adding a new item, we could split A and B into two nodes that are both half full. But we are adding a new item, so one of them is going to be even greater than half full. So it's easy to do that redistribution. In the odd case, if we weren't adding a new item, then it would not be possible to redistribute these nodes into two nodes and keep both of those two new nodes half full or more. But we are always going to be adding an item when we do this full node splitting. So we can end up with both of them exactly half full. And the only rule is that when we do this redistribution, everything in the left node has to be less than everything in the right node. So that's what we have ended up with here. So let's do a little example now where, kind of like in the last lecture, we'll build up a tree from scratch. But we have more items now, so we'll see some of the special cases that happen as we gain more levels in the tree and see how the tree evolves. So we'll add the items in that order, just A through G. And it'll be a ternary tree, so we'll have 3 pointers in an internal node and 2 keys in an internal node. And we'll also just say that a leaf node can hold 2 values. So we'll start down here with a new node. Even though it's the root node, I'll put it down there because it's going to become one of the lower nodes. And we can just start by putting A in there. And then we're on to B. We always try to fill up an existing node first, so we put it there. Okay, now when we add C, there's no room in the existing node, so we need to split it. So we'll make a new node. And then we need to redistribute A, B, and C such that everything in the left node is less than everything in the right node, and both of them have to be 50% full or more. So there are 2 ways we could do this. We could move the B over and put B and C in the right, or we could leave them where they are and put C, just C by itself in the right. In the last lecture, I kind of showed it the other way, where I favored the right side and filled it up more. This way I'll show it the other way, just to show that you can do it either way, just as long as you're consistent. So now that we have 2 leaf nodes, we need a new parent node. And I'll draw it over here to kind of leave room because there's going to be more stuff. So we'll have a left pointer going to there and a right pointer going to there. And then the question is, what's the key? And we pull up the smallest key from the right side in order to maintain the order property. Everything to the left of the key is less than it. Everything to the right of the key is greater than or equal to it. Now we add the D. We always try to fill up an existing node, so we can put it there. If we try to add C, we will traverse this tree down. If we try to add E, we will traverse this tree down, see that E is greater than C, so we would want to put it there in that node, but it's full, so we split it. and we'll put E over there, and we have a new pointer, so we need to pull up a new key. So we just pull up the smallest key from the right node. Okay, now we add F. We'll want it to go in this node, and there's room for it, so we do. Now, if we want to add G, this is where it'll start to differ from the example in the last lecture. We just proceed as normal. We would follow the tree down. We'd see that we'd want to put G there, since G is greater than the E key. So we'll split that node, and we put G in there. And now we need a pointer to it, though. So where does that pointer come from? There's not enough room for another pointer in the parent node, in the existing root. So we need to create a new node at this level. So normally we would pull up the G as the key for that new parent. And we now need to redistribute C, E, and G into two nodes. So if we did it the normal way, we would just leave that kind of as is. So we'll proceed for now. But now we need a new parent since we have two internal nodes. And now the question is, what key do I pull up for the parent? If we were following the normal procedure, I would just pull up the G and put the G into the parent. But we can take advantage of a little trick where in internal nodes, normally when we're pulling up a key, we copy something out of a leaf node. Since we need keys, all of the keys need to be in the leaf node, whether they're in an internal node or not, so we make a copy. But when we're pulling up a key from an internal node, we don't need to copy it. We can just move it. So the one that makes the most sense is not G. The one that makes the most sense is E, since it's in the middle of those two. We'd want it to be kind of the middle of the left and the right branch. So we can erase the E from where it was and just pull it up. And the reason we can erase it is because we already have E in a leaf node. So it's okay to just move it up. Now, this pointer right here, though, doesn't make any sense because E is gone. So all we do is give that pointer to the other sibling. So that is now a left pointer of G. And G's right pointer goes down there to that new leaf node. The new root node, E's left pointer, goes down to there, and its right pointer goes over to there. And you just kind of proceed in this manner, trying to add new items to existing nodes until they're full. When they do get full, split them. And a split in a leaf node can potentially trigger a split in its parent node and its grandparent. It could cascade even all the way up the tree in the most rare case. So now how do we handle deletes, and how do we maintain the 50% full rule when removing items from the tree? So let's say this is our current tree. We have two leaf nodes that are both greater than or equal to half full. We have the root node, which doesn't need to be greater than or equal to half full, but it happens to be in this case. But if we were about to delete H from this node, after removing it, the leaf node is now less than 50% full. So what do? We can't just delete the node because we still need to store that E in a leaf node somewhere. We can't move E over to another node because that other node is full. So what we do is we borrow an item from the sibling in order to refill the node that's now not full enough. So we pull over the D, and it would have to be the D since we need to maintain everything in the left node has to be greater than everything in the right node. So now we have two things on the left, two things on the right, and both nodes are now 2/3 full. However, this is no longer a valid B plus tree since the items in the right node have changed. This key up here is no longer correct. So we have to update the key now and just update it to be the smallest thing in the right node. So we just change it to D instead of E. Okay, now here's a special case. So starting with that same tree that we just made, after redistributing a few things, what if we were going to delete something else? So let's delete the B now. That would leave this node too empty. It would be less than half full. If we were to try to borrow something from the other node, let's say we pull the D back over, then this node would then be too empty. So we can't borrow from a neighbor. Redistributing is going to break the 50% rule for one of these nodes no matter what. But what we can notice here is we have only 3 items that need to be distributed. 3 items can fit in one node. So instead of a redistribution, we do a merge. And we just put all of the items into one node. So A, D, and E go into one node, and this entire node goes away. So it's not borrowing, it's merging and deleting a node. And now, look what's happened to the root node. It doesn't make any sense to have this key here since it only has a left pointer. There's no need for this extra level in the tree. So we delete the key D from the parent node, and now the root node is empty, so there's no need to keep it around. So we're down to just this tree. We got rid of one of the levels in the tree, and this is the new root node. And again, the whole point of this 50% full rule is to keep the levels in the tree as low as possible, keep the height of the tree as low as possible. So we went from a tree with 2 levels to a tree with 1 level. Now we can find any key in only one disk page access. But there's another special case here. We just saw that deleting something from a leaf node can cause a change in the parent. That change can also cascade up the tree, just like it can for adds. So it can cause changes in the grandparent, the great-grandparent, and so on. So let's look at another example. This tree is just barely full enough to maintain the half-full property. So all of these leaf nodes are exactly half full, and deleting anything from any of these leaf nodes would cause major cascading changes throughout the structure of the tree. So let's just see what happens if we delete this A over here on the left. If the A is gone, then this entire node becomes empty, so we can delete the entire node. If we delete that node, though, then there is no need for this key, since it doesn't have 2 children anymore. You don't need a key if there's just 1 child. So if we delete this key E, then this entire node is empty, so we can delete that entire node. But we can't just orphan this E that's in the leaf node. We need to put it somewhere in the tree. So we'll come back to that, but remember that we need to save that E. But if this internal node containing the internal E key is going away, then we don't need this key in the root node. And if that key goes away, then the entire root node goes away. So what we can do, and in order to save that E down there in the leaf node, is when a key goes away from the parent, we can pull it down into one of the children. So we'll pull it down into this node that also holds Q, but they need to be in order relative to each other. So the N will need to be on the left of the Q. So what we'll do is just take Q and both of its pointers and move them over 1. So we'll get rid of that pointer and move it over to this spot. So that pointer now goes there. We'll get rid of this pointer and move it over to this spot. And then we'll move the key itself. So we'll move Q over to there. Okay, everything in this right side of the tree is valid now. Everything to the left of Q is less than Q. Everything to the right of Q is greater than Q. And I've just kind of drawn it on top of the existing diagram. So remember, we're looking at the red pointers now, not the black ones. So now we've made room for N. So we can pull N down and put it right there. Right there. Now this black pointer here, though, that's been erased. So we need some pointer to the left of n. And that is where we can put E. So it turns out we can just take this pointer, and it now points to that stranded node. So it's no longer stranded anymore. And everything's valid now. Everything in the pointer to the left of n is less than n. Everything in the pointer to the right of n is greater than or equal to n. So remember, that's this pointer, not the old black one. And now we can delete that root node. So this is all kind of messy and drawn on top of an existing diagram, but in the end it looks like this. We deleted one item from one leaf node, and it caused the grandparent of that node to go away, and the height of the tree shrunk by 1. There are different ways you could have done this. So we could have actually ended up with, we don't necessarily need this key here or even this node here. We could have ended up with putting the E and the N into the same leaf node, kind of like that. It doesn't really matter as long as whatever you do is consistent. And you might argue that doing it this way would be better because it's fewer pages. But what's more important is reducing the height of the tree, because the number of pages you access during any traversal is equal to the height of the tree. So although we've reduced the pages by doing this, we're not going to reduce the number of pages you need to access for any query. And so let me erase this and go back to this. If we leave it this way, we now have more room to handle potential future insertions, where we won't have to split a node as frequently if we leave kind of more space available. We don't want to leave so much space available that the height of the tree is higher than it needs to be. So as long as we're keeping the height under control, then leaving some empty space can be good, because then we have room to add things without having to do an expensive split operation.